This video will cover 5.4, which is talking about the natural exponential function, or just simply e to the x. So we're going to talk about taking the derivative and the integral of e to the x, which that comes pretty naturally from just talking about the natural log of x, since e to the x is the inverse of natural log. Alright, so the derivative of e to the x is actually quite easy. It's everyone's favorite derivative because the derivative of e to the x is simply e to the x. So that's really, really nice. And so if I take e to the u, then that would be chain rule. So the derivative of e to the u would be e to the u times u prime. Okay, so now that we know this lovely derivative, let's try an example. So we want to write the equation of the normal line. Remember, normal means perpendicular to the tangent line, to the function e to the square root of x at x equals 4. So we want to take the derivative of this here, and we have e to the square root of x, so our u will be the square root of x. So g prime will equal the exact same thing, e to the square root of x, and then just simply times the derivative of square root of x, which is 1/2 x to the negative 1/2. Now, I want to clean this up because I'm going to be evaluating this, and so when I evaluate, I don't like negative or fractional exponents, so I'm going to rewrite this as e to the square root of x over 2 square root of x. Alright, so now that's my derivative, so I want to calculate if I want to do equation of the normal line. I need to find the slope at 4. So g prime at 4 is going to be e to the square root of 4 over 2 times the square root of 4, which will be e squared divided by 4. Now, since that's the equation, or the slope of the tangent line, we need to find the slope of the normal line, so we're going to take the opposite reciprocal of that, which is negative 4 over e squared, and there's my slope. Now, I also need to find the point, so at 4, I need to know what g actually is at 4. So g of 4 is e to the square root of 4, or just simply e squared. So to write my equation now, we have y minus my y value e squared equals my slope, negative 4 over e squared times x minus 4, and that is the equation of the normal line. So for example 2, all we're asked to do is just simply differentiate with e to the x. So we have x times e to the x, so that's going to be a product. So the derivative of x is 1 times e to the x plus x times the derivative of e to the x, which is e to the x, minus e to the x. And so then you'll see that e to the x here cancels out with negative e to the x, leaving us simply with x times e to the x. All right, our differentiation, it would not be complete without an implicit example. So let's look at this one. Find dy dx given the equation. So we have e to the xy. So when I take the derivative of this, e to the xy is going to simply be e to the xy. That is the derivative. Then I have to multiply that times the derivative of x times y using the product rule. So since I know that I'm going to have to apply the product rule, I'm going to have a sum. So I want to put big brackets there, meaning that e to the xy is going to have to distribute inside there. So the derivative of xy is 1 times y plus x times y prime. Keep going, plus 2x minus 2y times y prime, which then equals 0. So remember to find dy dx, or in my case, y prime. We first need to take this e to the xy and distribute. So that's going to lead us to get y times e to the xy plus x e to the xy times y prime plus 2x minus 2y times y prime. Okay, now remember with implicit, we want to take everything that has the y prime term and leave it on one side. Everything that's not a y prime term, move it to the other side. So when we do that, we get y prime. Oh, and I just realized an equal sign that should not have been there. Okay, so we have y prime, and then when we factor, we get x e to the xy minus 2y And then on the other side, we're going to get negative 2x minus y e to the xy. And then when we simply solve, we have to just simply divide. So then that's going to be over x e to the xy minus 2y. And then this goes away and becomes just y. Okay? Just a note here as well, this is totally fine for my final answer, but it's actually not like what the preferred form would be. So the preferred form would be for everything to be, for most things to be positive. So if I just simply change the sign of everything, then you're going to get this statement, which is probably more like what you would see on a multiple choice problem. For example 5, I'm actually going to, 4, I'm actually going to skip this for the video and then we'll do this in class. So we're going to move right along into the integral of e to the x. So if the derivative of e to the x is e to the x, then the integral of e to the x is e to the x plus c. All right, so then if I have e to the u with the u prime, or in other words, this u prime dx is really like du, then you will simply get e to the u plus c. You've got to have that u prime piece there. So let's look at some examples. So for part A, I have e to the 3x. Now that 3x, if there's anything other than x, then what needs to be u is that exponent again. So u is going to be 3x, and du will be 3dx. So then, to get just dx, du is 1/3 du of dx. So then the 1/3 can come out in front, the integral of e to the u du, and then that's simply 1/3 e to the u, which is e to the 3x plus c. Okay? So b, we have x cubed times e to the negative x to the 4th, and you can quickly see there that if u is negative x to the 4th, then you've got your du sitting right there as x cubed. So that's going to be negative 4x cubed dx, and if you divide by negative 4, you get negative 1/4 du equals x cubed dx. So then we have negative 1/4 integral of e to the u du, which will then become negative 1/4 e to the negative x to the 4th plus c. So you can see that it's pretty simple. When it gets more challenging is just figuring out what your u is going to be and things like that. So I'm going to have you try c by yourself. So pause the video. You can definitely do that one. And then we'll pick up and do d with me. Okay, so I'll show you what I've done for u and then du. So hopefully that makes sense. So when I find du, you just have to take into consideration that 2 here with 1/2. Continue on. And once you have your u and everything, e to the x is really that simple to take the integral of. So that's the only thing is finding that u. So looking at d now for a different example, this one's not quite as clear as to what you're going to use u, because if you use 2x as your u, then du is 2, and then I'm still left with something that will look like that. And you don't know how to take the integral of that because it's a quotient. So the u being 2x is not the route you want to go here. So remember that the derivative of e to the x is e to the x. So what I want to do here is make my more complicated piece be my u. So what I'm going to do is I'm going to knock out that whole quotient altogether and make u be the entire denominator. So watch what happens if that's the case. So then du would simply be 0 plus e to the 2x times 2, using the differentiation rules that we just learned, and then dx. And now you can see that that e to the 2x is sitting right here in the top of my integral. All right, so then that would be a 1/2 du equals e to the 2x. So then let's go over here, have 1/2 times the integral of 1 over u du. And look at that. What do we have? That should look very recognizable now from the last lesson that we did. This is now going to be a natural log. So we have 1 over u, so this is going to be 1/2 the natural log of the absolute value of 1 plus e to the 2x plus c. However, e to the 2x, or any e to the x function, as long as it's, oh goodness, as long as it's above the x-axis, is going to be completely positive. So we do not need the absolute value there, and that is not necessary. Okay, so now let's look at e. Looks a little strange because the numerator and the denominator are almost exactly alike. It's just one subtracting and one adding. So if you're going to make your u, you would either have the entire numerator or the entire denominator. So which one are you going to do? Well, if you made the numerator, then you'll get what you have in the denominator, but so the denominator is really 1 over that whole thing, which is not what you're going to have. So you're going to have to make u be the denominator, and what you're going to have is 1 over u, which you can note. So u, we want to be the denominator here. And typically that is the case, not with everything, but with a lot of things, u is going to be some form of the denominator. All right, so e to the x plus e to the negative x, and then du is e to the x, plus e to the negative x times a negative. So that's going to be minus e to the negative x, which you see we have sitting there in the numerator. So then this will become, that should be dx, so this will become 1 over u du, and that's very easy. The natural log of e to the x plus e to the negative x plus c. And actually for this one as well, this would still also be parentheses instead of absolute value. E to the negative x is still always positive, it's just decreasing instead of increasing. Alright, so for our last example, again, part of learning all these integration rules is also learning when to do what. So looking at f now, what I said for part E, as I said, when you have something really complicated, a lot of times u is going to be the denominator. But if you look at f, the denominator is very simple, e to the x. But if you see in the numerator, everything's in terms of e to the x. And the denominator, here's the key, is one single term. One single term that's in the same format, being e to the x, not a polynomial or a trig function. It's in the same format as the numerator. Now, the reason I couldn't do that with e is because we had 2 terms. All right, so if you have one single term that's in the same type of function as the numerator, then what you want to do is not necessarily use substitution, but you want to divide by that single term. So I want to take each of my terms in the numerator and divide by e to the x. So e to the 2x divided by e to the x would be just simply e to the x, plus 2 e to the x over e to the x, which is 2, and then 1 over e to the x will be e to the negative x. And so now you have something that you don't even have to use u substitution with. So make sure you look out for those types of formats. So the integral of e to the x is e to the x, plus 2x, minus e to the negative x, plus c is my answer. Okay, for the final example, I'm going to show you another integration technique along with the e to the x. So if you look at this antiderivative, it says find the antiderivative in 2 ways. So part A and then part B are 2 different ways. But before we do that, I want you to look at this integral and so apply what we were talking about before. Don't write this down, just watch. If I make u be 1 plus e to the x and du is e to the x dx, that didn't help me out at all. So that looks like it's not able to take the integral, so we have to do something, but we can. So we have to do something different. This is not going to work, and really at this point no form of u is going to work. So this is a new type of integration technique that I'm showing you here. So what we have to do is we have to manipulate this integral and make it look different without being technically different. So the two ways that we can make something look different and manipulate that and play with it a little bit is either add 0 or, in part B, multiply by 1. Okay? Because if I add 0, you're not changing the actual expression at all. And same with multiplying by 1, you're not changing the expression. So let's see how this looks. So if I add e to the x minus e to the x to the numerator, remember when I took u to be 1 plus e to the x and du was e to the x? Well, my problem was I didn't have an e to the x in the numerator, so let's put one there. So if you put one there, oh, there we go. If you put one there, then you have to also subtract 1 there. So we're going to add e to the x minus e to the x to the numerator. So I'm going to say 1 plus e to the x minus e to the x. And essentially, I'm not changing the expression at all because that's just something 0. So now, how this works is, what I can do now is I can split this up into 2 parts that will be able to take the integral of. So if you see, you have 1 plus e to the x over 1 plus e to the x, and that's simply going to become 1, so that's nice. And then also, if I have that subtraction of e to the x, that's also going to go over 1 plus e to the x. So look for a second at how I did that to split that up. And so now this is still the same thing as what my original integral was. So the integral of 1 plus e to the x over 1 plus e to the x is just the integral of 1. And now over here, you see that I have what I originally had with my u as 1 plus e to the x. And now that works out for me. So that's going to be the integral of 1 over u du. So integral of 1 dx is x minus natural log of 1 plus e to the x. No absolute value needed, since that is always positive, and this is my answer. Okay, so that's one way of looking at it. If you have something that truly cannot be integrated using u, then try adding 0, clever form of 0, or multiplying by clever form of 1, as we'll see in part B. Okay, so same problem, but we can approach it a different way by multiplying by a clever form of 1. So you see here that my clever form of 1 is not e to the x over e to the x, it's e to the negative x over e to the negative x. And the reason being is if I were to multiply, I just want to show you, again, don't write this down, just watch. If I were to multiply by e to the x over e to the x, you get e to the x over e to the x plus e to the 2x. And so what that becomes is having this e to the 2x and this e to the x actually makes the problem more complicated, and that was not my goal. So I don't want to make the problem more complicated, I want to make it more simplified. So if you watch and see what happens if I multiply by e to the negative x, what's going to happen is when I multiply that e to the negative x with the e to the x, they're going to cancel each other out. So if I multiply by e to the negative x, you get e to the negative x over e to the negative x, and then e to the x times e to the negative x simply becomes 1, because the x minus the x becomes 0, and e to the 0 is 1. All right, so we're going to take the integral of this piece then, and so now it's pretty easy to see what we're going to do. We're going to make u be e to the negative x plus 1, so du, or dw, du is equal to negative e to the negative x dx. All right, so then when we substitute, we have a negative out front because of this guy. Integral of 1 over u du. So then that is the negative natural log of, hold on. Yes, that's correct. Let's keep going. So the negative natural log of e to the negative x plus 1 plus c. Now, remember that we did both of these problems, and they start out with the same thing, but if you look, we've got slightly different looking answers here. So I just want to show you that they are actually equivalent, and I'll show you how you're going to do that here. So this negative right here, remember if you have a multiple out in front of natural log, you can make that into an exponent on the inside. So that's going to be the natural log of really the inverse. So 1 over e to the negative x plus 1 plus c. And then now applying our natural log rules, that's going to be the natural log of 1 minus the natural log of e to the negative x plus 1. And actually, I took this step too quick. Sorry. So not that line. So actually, before doing that though, because you could see with that line that still didn't get us back to what the first problem looked like. So what we can show you is 1 over e to the negative x plus 1 is actually the same thing. Again, if I multiply by a clever form of 1 here and make that positive e to the x, that would be e to the x over 1 plus e to the x. Okay, here we go. This is working out now. All right, so that's going to be the natural log of e to the x minus the natural log of 1 plus e to the x plus c. And natural log of e to the x is simply x. And that should be now what we had up in the top. All right. Now, the good news, Now, the good news is typically you will not have to do all this because that's pretty tricky and hard to see if it's not shown to you. But I just wanted to do that for you so you could see that they do actually turn out to be the same integral. All right, so as we learn more integration and differentiation rules, we learn more techniques on how to actually integrate. So in class, we'll do that other example that I skipped and get some more practice.